Hi everyone. So today I'm going to do a couple of questions. One of them is going to be a center of mass problem, which is part of this week's assignment, and the other one is going to be a rotational motion problem, just kinematics, which is for the video that you saw, I guess, on Tuesday. But it's not part of this assignment. That'll be part of next week's assignment. Okay, so we'll just do two questions today. But before I start, I wanted to address you guys. I guess let me see how many people are here. Well, there's only four of you. That's okay. I'm going to be sending this out in an email anyhow. I wanted to change the format of the class next semester a little bit. It turns out that I'm going to be teaching it online again. I really didn't want to have to do that, but there's no indication that the COVID restrictions are going to change anytime soon. And in fact, I think they've just become stricter again because of some mandate from the state. I mean, this isn't Juvo College's doing. Juvo College is just responding to what they're supposed to be doing. But I hate the idea of, like, changing formats halfway through. So for the same reason that I didn't do an in-class this semester, I'm not going to do it again next semester. But I got to tell you that I really dislike teaching this way. I much prefer teaching in person, and the information is the same. It's just the quality of the education is different. And so I'm going to try to approximate that a little bit better next semester. I mean, one of the reasons for having these live chats was so that it was as close as possible to being in a classroom, okay, where you could ask questions, although, you're not asking them verbally, you would type them into the chat. Um, there were reasons for doing it this way and not using Zoom. I won't get into that, but I think that next semester I want to do a couple of changes. First, the live chats, people do show up to them, but not that many. Okay, you could see that right now I only have four, and the live chats have been not been as well attended as they could have been. So because people, what they'll do is they'll they're recorded, they're up on YouTube, they can watch them later, and that's perfectly fine. And I want to give people that flexibility. But at the same time, you have to be able to have access to me. So what I was thinking was next semester to get rid of the live chats and do 3 hours of pre-recorded lectures, but then have 3 hours in the evening sometime when we could meet together in person at the college. Okay, this isn't written in stone. I'm going to suggest this in an email next semester. You could think next week. You could think about it and give me feedback. What you think about the idea. But basically, just instead of the pre-recorded, instead of the live chat, you would have a pre-recorded lecture. But at the same time, you would have opportunity to, like, be physically with me in a classroom at the college. Ironically, I live just 2 blocks from the college. I'm within walking distance, but I'm never there. I'm always just teaching from home. This way, and it's optional. This evening, I wouldn't call it a class, evening tutorial or seminar, whatever. It would be optional. You don't have to go there. What it would be is I would go there and I would answer any questions that you have first. If you have no questions, I'll just generate problems like I do right now. So, if you came there and you said, "Oh, I don't have anything, but I want to see what he does," fine. I can produce problems of the kinds that you would see on tests or on assignments and so on. The assignments would be the same. They would be online. The tests would be the same. They would be online. It's just that I would replace this with a pre-recorded lecture and then make myself available physically in a classroom once a week for about 3 hours in the evening, or up to 3 hours in the evening, depending how long we take, and still be available for those nights of the week when I can uh, be available via Google Hangouts. Okay, so you'd have access to me in all possible ways. All right, and of course email as well. The only other thing I would change, and for a different reason, is I'm going to change the rules for the test. Right now, if you miss a test, that's it, unless you miss it for emergency reasons. Okay, but you miss it for non-emergency reasons, it's a zero. I was, some people did, and I was not able to really deviate from my rules. It's not a question of being strict or cruel. It's that I have to be consistent with the rules, because if I change if I propose that these are the rules and people make decisions on those, and then I change them for some people and not other people, that's not fair. And so I think next semester what I'll do is maybe something like, if you miss the test and you take it later, for every day that you take it later, it's 10% less off of the maximum grade that you get, something like that. I haven't fully worked it out, but I have to be fair to everyone. I hope people understand. You might say, well, that doesn't apply to me, and it doesn't apply to like 99% of the people, but there were people that made decisions based on my syllabus, and then other people missed the test, and I had to follow through on my syllabus. Well, that's why I do that. Okay, so I just wanted to be very clear and upfront about that. So those will be probably the two changes. Neither of them are written in stone, and so next week I'll send out an email to people and just get some feedback from people and say, yeah, I like that. No, I don't like that. I'm trying to figure out the best way to give you the best of all worlds. Like, if the way online courses work, like I say, I give you those emails every day, and I say, this is what you should be doing today, this is what you should be doing today, and you can move it around in your schedule, and people like that because you work, you have other time commitments, but at the same time, I really want to be available. Otherwise, it's just throwing a textbook at you and say, here, learn it on your own. The whole point of a college course is to be in contact with a professor that's an expert in their field and is able to look at students and personally help them through whatever difficulties they might be having. And that's not so easy to do through this environment, which is very rarefied. I mean, you're there at the other end. You're 30 seconds behind when I speak. I have to look over at the chat. I mean, it's not as good as it is in real life. We have to admit that, okay? And I got to be honest, I'm really tired of this new abnormal. So we'll see. So just keep that in mind. I'm going to take a look at the chat here and see if I've gotten any feedback so far. So um, no one said anything, but just keep that in mind, and um, you can always send me an email afterwards. All right. Well, let's start then with the question. So the first question is a center of mass problem, and these are pretty easy. And the center of mass problems that I gave you on the assignment was a 1D problem and a 2D problem. And I actually tried to draw pictures for you, which were like ASCII diagrams, but you really don't need them. These problems are easy enough to solve even without them, and I'm going to do that. I will show you the diagram at the end, but you don't really need a diagram. They're easy enough. The diagram is useful to see if your answer makes intuitive sense, but just mathematically, these are pretty easy problems to solve. So let's take a look at this first problem. I've got four masses here. Let me just indent them. Whoops, that's not it. That's indent. There we go. Okay, so I've got a 3 kilogram mass, and it's at this point in the xy plane. It's at x is equal to negative 1.3 meters and y is equal to 1.4 meters. And then I've got a 4 kilogram, a 5 kilogram, and a 1 kilogram mass. Okay, and I ask you to calculate the center of mass in this two-dimensional plane. Okay, and well, how do you do that? All right, so like all of our problems, which are vectors, if you separate the x and the y components, in other words, you work in Cartesian, the x and the y completely decouple. Okay, so the formula for only involves x information, and the formula for y only involves y information. Okay, and so to calculate the x component of the center of mass, it's well, let me scroll it up. It's this formula right here. Okay. So what does that formula say? So x is this capital X here. That's the x component of uh, the center of mass, and it's equal to m1x1 plus m2x2 plus m3x3 plus m4x4 plus m5x5, however many there are. Basically, you multiply m times its x component and then just add them up for all the masses you have. Well, here we have 4. That's why I put dot 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 there, just to indicate, if you had more, we only have 4, but if you had more, you would just do it for all of them. And that gives you the numerator. Okay, then the denominator is just the sum of all the masses. All right, now if you've ever done statistics, a statistics course, this is an average. It's what's known as a weighted average. Okay, so what a weighted average means is like your x and your y, your x1, your x2, x3, they all contribute, but they contribute differently depending on what the mass is at those points. Okay, that's why it's called a weighted average. All right, and that's actually how your grade is calculated, something like that. I simply weight the various pieces according to what I specified in the syllabus, and that's what gives you the final grade. Okay, so here's m1x1, and then you add m2x2 and so on. So m1 is 3 kilograms, and x1 is the negative 1.3. Okay, so there it is right there. Right, and then m2 is 4 kilograms, and x2 would be this number right here, 0.95, 4 times 0.95. Same thing for x3 and x4, okay? And notice there's no y information used at all, okay? So no y information there at all. So you just add up m1x1, m2x2, m3x3, and m4x4. Divide that by the sum of all the masses, 3 plus 4 plus 5 plus 1. Okay, they're like that. And just work it out, and it turns out to be 0.742 meters. Okay, that's the x component. All right. So, well, what about the y component? Same formula, just replace your x1 with y1, your x2 with y2, and so on. All right. So here's that formula right here. Okay. And how do you substitute in? Well, this isn't a typo here. If you take a look at the what I did for x, there it is. But you see where I have the blanks here? Just take out all the x values. The rest of the everything else is the same. Okay, and you just replace your your x1 that was there with your y1, 1.4. So if you go back up here, so what was the 3 kilogram mass? What was its y component? 1.4. So it's 3 times 1.4 right there. Whoops, right there. And then 4 times negative 1.3. Okay, so 4 is that y is equal to negative 1.3. There it is there. And same thing for m3 y3 and m4y4. All right, and working that all out, you get a y component of negative 0.135 meters. Okay, and that's it. That is the answer. So you could see that you could do that without any diagram. It's just basically you calculate your x component based on the weighted average of the x values, and your y component based on the weighted average of the y values. Okay, a diagram still is useful though. I'll show you that in just a second. The diagram is useful because it helps you to see if your answer makes sense. Okay, so let's switch to that diagram. Okay, so what I have drawn here is an approximate position for where all the masses are. Okay, so the 3 kilogram, you could see it right there. It was what did I say here? It was at negative 1.3 and 1.4. So I just eyeballed this. So if you go over in the x direction here, let me do this in blue. Okay, 1.4 this way, and then you go up this way, 1.3. Sorry, negative. What was it? Negative 1.3. And let me do that again. So you go this way, negative 1.3, and then you go up 1.4. You get to the 3 kilogram. Okay. Whoops. I erased something that I shouldn't have. All right. So there's the 3 kilogram. There's the 4 kilogram. There's the 5 kilogram and the 1 kilogram. Okay. Now, where did we find the that the center of mass was? So the center of mass, it's not in the geometrical center because it's a weighted average. And what that means is that the 5 kilogram and the 4 kilogram, they're gonna pull the center of mass more towards them than the 1 kilogram or the 3 kilogram. Okay, so the bigger the mass, the more it tends to pull the center of mass towards it. So the closer the center of mass will be. So the center of mass will be closer to the 4 and the 5 and the 4 than it will to the 3 and the 1. All right, and we found out that its x component was 0.742. So just eyeballing that here, this tick right here, that's the 1. So this would be x is equal to, about 3/4, 0.74, like that. Okay. And for the y component, we found that it was negative 0.135. So that's pretty close to the, just below the x-axis, like somewhere around here maybe, like that. Okay, and where the two intersect, that dot right there, there's your center of mass. Okay, and so you say to yourself, well, does it make sense? Yeah, and you can see that it's being kind of pulled towards the 5 and the 4 there. The 3 is a little bit further away, and the 1 is, it's closer to the 4 and the 5 than it is to the 1 and the 3. All right. A few things you could say, is that the center of mass would never be outside of the shape. And you say, well, what shape? So if I were to draw, if I were to draw, like the perimeter of this shape, like that, just join the outsides there, like that. Okay, the center of mass has to be within that red region there, the closed red region. If you had a center of mass out here with these guys, there's no way, because you would say to yourself, well, there has to be a mass up here that's trying to pull it towards it, and you go, well, where is that mass? Well, there's no mass out there, so the center of mass would never be outside of that. Okay, and similarly, if you found a center of mass that was like here, close to the 3 and not the 4 or the 5, even if it's inside of that red shape there, again, that would be wrong, because the 4 and the 5 would tend to pull it closer to them than the 3 would towards it. Okay, or the 1, or even worse, like if you found it like down here, you go, oh, that looks pretty suspicious, because it should be closer to the 5 than it is to the 1. Okay, and so you would say to yourself, yeah, that's not right. Okay, and so yeah, that kind of makes sense. I mean, it's not proof, but at least it's intuitively in the right ballpark. Okay, so there you go. There's our center of mass problem, 2D center of mass problem. There really isn't that much more to it, and the only other thing you need to know is, like, what does the center of mass even mean? How should I think of it as in my head? I mean, like, not just where is it, but what is it? And it's basically like, if I were to throw something and it were to freely spin, it would spin around the center of mass, okay, or an axis through the center of mass, okay. Or we'll see this next semester, when I go to balance something. If I put my finger under the center of mass, there it is. My finger now is underneath the center of mass of my remote, okay? So it's not at the center of mass, but the center of mass is above it, or my finger is directly below it, okay? And that's why it's balancing. And that's actually our first topic next semester, is going to be on statics, okay? Which is very important for people who are like pre-PT or ESS, because it's, center masses are very important for the dynamics of the human body. Okay, and also I can't demonstrate this. I throw this up in the air, it spins. Okay, if we were physically together, I do, because I throw my eraser, my whiteboard eraser around, and you see that it spins, and it spins around its center of mass. Okay, and that's actually not that hard to even experimentally verify. Okay, so that's the interpretation of the center of mass. Up to when we did up to rotational motion, we treated all the motion, all the dynamics that we've done in the course up to rotational motion as basically the motion of objects that are not extended in space. And as soon as you start to talk about objects which are extended in space, then the center of mass becomes very important. Okay, so that's why the center of mass is kind of transitional between conservation of momentum and our next topic, which is rotational motion. Okay, so rotational motion, is like the motion around the center of mass. Well, not necessarily just the center of mass. I mean, if this thing were freely spinning, it would spin around the center of mass. But I could force it to spin around some other axis. Like, this thing would wanna, like if I threw it up, it would wanna spin around the middle here like that, somewhere in the middle here like that. Okay, but I could just grab it at an endpoint here like that and say, I'm gonna force you to spin around this point here like that, like a door, door on hinges or whatever. So, when we talk about rotational motion, it could be rotational motion around the center of mass, or it could be rotational motion around any point, or any, I keep saying point, but any axis that I force it to rotate around. Okay, and so for this week, I just had you watch the kinematics part of rotational motion, and next week I'll have you watch the rest of that video, which is on the dynamics. I didn't know how the course would split up. I mean, in retrospect, I probably should have split that video in two, but I at the time it just didn't seem like, it seemed like it's something that we could have done over 1 week, but it didn't turn out that way. Didn't want to overwhelm you with stuff, so just did the first half of it. Okay, so here's our problem on rotational motion right here. Okay, so a centrifuge, what is that? I don't know if you've played with them in biology or in chemistry. They tend to be used more in biology, or in any of the health fields. If you have like a test tube with, say, human blood or something like that, and you want to separate it out into its various parts, you put it into these centrifuges and they spin. And as they spin, they produce a lot of centripetal acceleration, okay? And that separates out the stuff. The heavier stuff will go to the bottom of the test tube, and the lighter stuff goes to the top of the test tubes, okay? These things spin very fast, and I actually looked one up on Amazon, and so these numbers are all real, except for the 45 seconds, okay? That's the only thing that I couldn't determine from their specification, but the rest of this is all like an actual centrifuge that you could buy. Okay, so the centrifuge starts at rest. Okay, so I don't know if you've ever seen them. You put test tubes in them, you close the thing, and then they're at rest, and you flip the button, and then they start to spin. Okay, so it starts at rest, and it spins up to 5,000 RPM. RPM stands for revolutions per minute. Okay, so it spins up to 5,000 RPM, and I estimated that it would take 45 seconds to do that. Okay, so that's the only number that's not real in this whole problem. All right, so, or I don't know if it's real or not. But it's the only one that I guessed at. Okay, so starts at 0, and it starts to spin faster and faster and faster and faster and faster and faster until it spins up to 5,000 RPM in 45 seconds. Okay, the bottom of the test tubes actually experience, because they're in like at an angle. There's the top up here and the bottom down here. The bottom, which is the furthest from the axis that it's spinning around. Okay, the bottom of the test tubes experience an acceleration of 3,074 g at maximum speed. Okay, now what that means is g is the acceleration due to gravity. We'll estimate, round off to 10 meters per second squared, as we have. Okay, so that's pretty fast. I mean, when you drop things, they accelerate down at 10 meters per second squared. Okay, well, in this test tube, these things are experiencing an acceleration which is 3,000 times more than their weight. Okay, so humans will pass out at 9 g. All right, so that's like 9 times your weight. So if you're in a jet or something like that, and the jet is doing some extreme accelerations, a 7 is already pushing it, but by the time you get to 9, you're in a lot of distress. Okay, and so 7 to 9 g's is about all that we can take. This is 3,000 g's, so I pity any bacteria or any other cells that are in this. They're going to get squished under this kind of an acceleration. But that's an actual number. That's actually what this particular centrifuge was rated at. Okay, so the bottom of the test tubes experience an acceleration of 3,074 times the acceleration due to gravity at maximum speed. Okay, and I also said assume that all this motion happens at constant angular acceleration. So then I ask a few questions. What's the angular acceleration as it spins up? Okay, how many times does the centrifuge turn during the first 45 seconds? So it starts at rest, and then it spins up, spins up, spins up. By the time it's finally spun up, that takes 45 seconds. By the time it's spun up, how many times did it turn? Okay, the centrifuge, when it's spun up, has a centripetal acceleration. What is the centripetal acceleration at maximum speed? Okay, and how far is the bottom of the test tubes from the axis that it's spinning around? Okay, we'll be able to answer that too. All right, so okay, let's start off with the first one. What is the angular acceleration? All right, so this is assuming constant acceleration, so there's actually 3 formulas, and here they are. Okay, and the first formula is Well, all three formulas are just like our 1D kinematic formulas, but the 1D kinematic formulas I gave you way back at the beginning of the semester, they were like linear along a line. These are the same formulas, but now in rotational motion, but they have the same structural form, okay? Because the mathematics is the same. I didn't quite go over to how they were derived, but if you went through their derivation carefully, you would see that the derivation for the linear version and the rotational motions, which we're going to use now, they're actually the same. It's actually the same derivation. Okay, and uh, let's take a look at those equations. So equation number one, I don't think this is exactly how I gave it to you on when I did the pre-recorded lectures. I probably gave it to you like this. Okay. And this equation is just like our old equation, x is equal to 1 half at squared plus v naught t plus x naught, but now it's in terms of angular motion or angular quantities, okay? So instead of x, you have theta, instead of v, you have omega, and instead of a, you have alpha, okay? Theta is the angle, omega is the angular velocity as opposed to the linear velocity, and alpha is the angular acceleration as opposed to the linear acceleration that we used before. Okay, so there's the formula there. So here's alpha and here's omega. It's actually omega naught the initial. And there's theta and, there's theta and there's theta naught. So there's the initial angle and there's the final angle. Well, we usually don't think in terms of an initial and final angle. We usually think in the terms of how much it turned or what the change in the angle was. And so if I take this and I subtract theta naught from both sides, then this equation becomes this, like that. And theta minus theta naught there like that, that's just your delta theta. That's just delta theta, it's like the change in the angle. And whoops, and that's how I got this equation here. So that is equation number one, but it looks slightly different than the way I might have given it to you. So I just thought I wanted to explain how you got the delta theta in there. Okay. So, all right, there's equation number one. Equation number two is omega is equal to alpha t plus omega naught. So if you start with some initial angular velocity and you have some angular acceleration applied for some time t, you come up with some final angular velocity. So that's your final omega. There's your initial omega. And then finally, equation number three, just like before, it's equations one and two with the time eliminated. So basically, solve for time here, plug it into there, and you would get equation number three. Equation number three is useful for problems where you don't know the time. Again, it's just like we had previously with our linear quantities. Okay, so what's the angular acceleration? So if you look through these equations, you say, which one can I use? Well, what do you know? Let's take a look at the problem again. It starts from rest. What does that tell you? So omega is your angular velocity. If you're starting from rest, that means that your initial angular velocity, or your omega naught, is 0. Okay, that's what that means. So we know omega naught. And it spins up to 5,000 RPM. Okay, so what's that 5,000 RPM? That is omega, that's the final angular velocity, in the wrong units, but still, it's the final angular velocity. That's omega. So we know omega naught and we know omega. What else do we know? We know the time. Okay, and then there's some more information, but it doesn't really help. Okay, at least not at this point in the problem. All right, and so if we go down here, we take a look at these and we say, could we use equation number one? Well, not really. We know t, we know omega naught, we know t, we don't know alpha. That's what we're trying to solve, the angular acceleration. So we're trying to solve for alpha. And we don't know delta t. We don't know how many times it turned in that 45 seconds. In fact, that's the second problem. Okay, and if you take a look at number two, do we know omega naught? Yeah, that's rest, 0. Do we know omega? Yeah, that's at 5,000 RPM. Do we know t, 45 seconds? Yeah, so you know everything except for alpha. You can solve for alpha. Okay, so great. Let's use equation number two. So here I just state what I said already. The initial angular velocity is 0 radians per second. So we have to work in radians per second in here. You say, well, why not degrees or some other units? And the reason is the formulas, which I'll show you in a little bit, that convert from the linear quantities to the angular quantities or vice versa. They only work in radians. Okay, and so for these formulas to work properly, it's best that you just work in radians. Okay, so 0 is easy because if you're not rotating, it doesn't matter what the units are, it's 0, so it's 0 radians per second. But 5,000 RPM, that's not the right units. Okay, so RPM means revolutions per minute. Revolution is just another word for turn. Okay, so it's like turns per minute. Okay, so how many times does this thing turn per minute? Well, it turns 5,000 times per minute once it's spun up. Not when I first turn it on. It takes a little while. It takes 45 seconds. But, after 45 seconds, it spins up to 5,000 turns per minute. It doesn't spin any faster than that. It just gets the 5. So it spins up to 5,000 turns per second, and then it continues at 5,000 turns per, it's not per second, per minute. Okay, so 5,000 turns per minute is a lot. Okay, um, a minute has 60 seconds, so this is much, there are many turns per second here. Okay, so we can't work in revolutions per minute. We have to convert from revolutions per minute to radians per second. So a revolution measures an angle, and a revolution, a turn, is an angle. So your brain usually doesn't think this way. You think of a turn as a turn and an angle as an angle, because you usually think of an angle as kind of a wedge. Okay, you say, well, what's the angle within that wedge? And a turn is like, you think of a turn like that. Okay, but a turn is an angle, and I say, well, how am I supposed to think of that? How can I conceive that? And it's this, if you make like, if I say to you, make a quarter of a turn. So I've got a circle here like that. A quarter of a turn, what is that? 90 degrees. Or I say, do half a turn. Well, half a turn is 180 degrees, you see? And so when you talk about fractions of a turn, you're talking like, 90 degrees, 180 degrees, whatever that fraction is. And that's in degrees, okay? Same thing in radians. If I say a quarter of a turn, what's that? It's pi by 2 radians, okay? Or if I say half a turn, what's that? That's pi radians, okay? And so a turn is actually an angle, and an angle is a turn, okay? So if you say like 45 degrees, what's that? Well, 45 degrees, 90 degrees is a quarter of a turn, so 45 degrees would be an eighth of a turn. So, the fraction of a turn is an angle, okay? And we say, well, what if I have 2 turns? Well, then that's just 360 and then another 360. Or if you're talking in radians, it's 2 pi and then another 2 pi. And so what an angle is and what a turn is the same thing, okay? And so when you say a revolution, you go, okay, well, revolution is a measure of an angle, all right? It's more than one turn, but that's okay. An angle can be more than one turn, okay? More than one complete revolution around the around, okay? So how do you convert that? Well, one revolution, that's in the numerator, so I'll put 1 revolution in the denominator here. 1 revolution is equal to 2 pi radians. Okay, so this fraction will eliminate the revolutions and replace it with radians. Okay, and then over here we have minutes. Minutes are in the denominator, so I put minutes in the numerator there like that. And of course we want to go from minutes to seconds, and 1 minute is equal to 60 seconds. Okay, and so if I work that out, that turns out to be 523.6 radians. Okay, 523.6. Roughly speaking, to go from revolutions to radians, it's like dividing by 10. Not quite, but just to see that you're in the right ballpark, we started at 5,000. Your answer in radians per second should be around 500. Well, it's actually 523.6. Okay, so just to give you an idea, just to make sure that you're going in the right direction and you didn't convert incorrectly here. Okay, so revolution per minute is about 10 times more than a radian per second. Okay, so there we go. We got omega naught. We now have omega, and we have t was 45. Here's the formula. Okay, we plug in, we solve for alpha, and we get 11.6 radians per second. Okay, so there you go. That answers our first question. What is the angular acceleration? Okay, and so what is that angular acceleration? What does it mean? How should you picture it? So it's not how fast it's turning, but how fast it's speeding up. Remember, it starts turning slower, and then it turns faster and faster and faster and faster, 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 faster. That alpha is a measure of how much it speeds up. Okay, omega is just how fast is it turning. So if it's turning at a constant rate, that's omega. That'll tell you that. Okay, and alpha tells you not just how fast it's turning, but how fast it's speeding up. Okay, great. That's the first one. Second one, how many times does the centrifuge turn during the startup time of 45 seconds? Okay, so you say, well, how many times does it turn? And you ask yourself, what is it asking for? Because it has to be in terms of one of these variables up here, right? So how many times does it turn? Well, in your mind, again, turn and angle should mean the same thing. So how many times does it turn? That's your delta theta. Okay, now it'll come out in radians, but you know that 2 pi radians is 1 turn, or more precisely, 2 pi radians is 1 revolution. Okay, and so what we're really solving for is theta. And you say, well, okay, well, which equation should I use? Should I use equation number 1? You can't use number 2 because we're looking for delta theta. Okay, can we use number 1 or can we use number 3? Either one of them at this point will work. Okay, because we have all the we have alpha, so we could use either number 1 or number 3. I use number 1 because it just seemed like the easiest one to use. But you could check later. If you do it with number 3, you better get the same answer, otherwise something went wrong. Either I did something wrong or you did. But all 3 equations have to be consistent. Okay, so using number 1 here, there it is. We'll substitute in. So alpha we now know because we just solved for it at 11.6. There it is. Okay, t is 45 squared. Omega naught is 0, so 0 times 45, that's 0. All right, and that turns out to be 11,745 radians. Okay, now that is a correct answer. But like on my multiple choice test, you might look and you might not find any radian answer there. You might find the answer in terms of revolutions. And that's more kind of loyal to or consistent with what I'm asking here, because I'm asking how many times did it turn. And so you might say, oh, well, he wants the answer in number of turns or number of revolutions. So if you get your answer in radians and you say, well, I don't want it in radians, I want it in revolutions, what do? Convert. So here, there's the angle, there's the fraction to convert, okay? So we got radians in the numerator here. We'll put radians in the denominator there, okay? And we want to convert from radians to revolutions, so we'll put revolutions in the numerator. 1 revolution is 2 pi radians, and that turns out to be 1,869.3 revolutions, okay? So not 45 seconds as it spins up, this thing is going to turn about 1,870 turns. Okay, that's quite a bit in just 45 seconds. Okay, and again, a centrifuge, they spin very fast, and so yeah, you can expect that it makes a lot of turns as it spins up. Okay, let me see if there's any questions in the chat. No, everyone looks like you're okay. All right, and so now question number C was, what is the centripetal acceleration at maximum speed? So this is a bit of I wouldn't say it's a trick question, but I could see how you might get tricked. Let's go back to what I tell you here, okay? And so if you read the question again, you say, well, what formula should I use? What information do you give me and what formula do I use? That's usually what students will do. Sorry, let me scroll down a bit. That's usually what students will do. They'll think, what formula do I need that has centripetal acceleration? But you know what? I indirectly give it to you in this problem, because the centripetal acceleration is that 3,074 g. Okay, so what is the centripetal acceleration? Well, when something spins, remember when we did uniform circular motion? So rotational motion is just a generalization of uniform circular motion. It's not like they're two different things. It's just that rotational motion is uniform circular motion plus more possibilities. Okay, it's more general. And in uniform circular motion, that whenever you're going on a circle, there has to be an acceleration towards the middle. That's what turns you. Okay, if there were no acceleration, you go in a straight line. So because you're turning, there's an acceleration. That acceleration which turns you is called the centripetal acceleration. It's the acceleration towards the center. That's what a centrifuge is all about. Okay, now I won't get into this business of centrifuge versus centripetal, centrifugal versus centripetal. Those are just misnomers. Okay, I don't want to try to fix a muddle that shouldn't have existed in the first place. But there's an acceleration towards the center. It's called the centripetal acceleration. That is the acceleration that is doing the separating out in a centrifuge. Okay, it separates out the various layers of blood. Okay, so what is that? Well, it turns out to be 3,074 times g, and a g is 9.8 meters per second squared, which will round off to 10. Okay, and so down here for part C, there's nothing magical. There's no formula for it. We just say, oh, well, you told me that it's 3,074 times the acceleration due to gravity, which is 10 meters per second squared. And so the centripetal acceleration experienced in in this test tube, or at least at the bottom of the test tube, is 30,074 meters per second squared. That's a lot, okay? Like I said, that's like 3,000 times the weight of whatever's in there, okay? So there you go. There's the centripetal acceleration. Okay, I know there are formulas that involve centripetal acceleration, but don't go looking for these formulas. I mean, I gave you that information. I just gave it to you in a non standard way. Okay, and this is exactly I got this directly from the Amazon.com page for the um, centripetal centrifugal centrifugal centrifuge. Sorry. Okay. All right. Part D, how far is the bottom of the test tube from the axis? So I don't know if you've ever worked with one of these, but the test tubes, they sit in there a bit of an angle like this, okay, with the opening closest to the axis and the bottom furthest from the axis, and it's at the maximum acceleration is obtained at the bottom of the test tubes. So that's why I ask, how far is the bottom of the test tubes from this axis? Okay, and you might say, well, how much should that be? I couldn't find the number there, but it can't be, can't be a meter, it can't be 2 meters, because these things, they're fairly small, they're like that. Okay, and so you say, well, what formula do I use? So there are two accelerations when we're talking about rotational motion. Okay, so for uniform circular motion, there was just the centripetal acceleration, the acceleration that kept you on a circle. You want to go straight, but you're turning, turning, turning. That turning is always a turning towards the center, okay? And that turning towards the center is centripetal, okay? And that's why it's called the centripetal acceleration. But for rotational motion, there's also the acceleration along the outside, and that's called the tangential. So we have two. We have the centripetal, and there's its formula in terms of angular quantities, omega, and there's the tangential, and there's its formula in terms of angular quantities. Okay, it turns out that AT, even though I didn't ask for it, I'll calculate it in a minute, it's small, and it's not what we want. It's not the tangential acceleration that is responsible in a centrifuge for separating things out. Okay, it's the centripetal. Okay, in fact, once this thing spins up to its maximum speed and it's not spinning up anymore, then AT is zero anyhow. Alpha is zero, and then AT is zero. Alpha is just non-zero as it spins up. But once it gets to that 5,000 RPM and it's not going above the 5,000 RPM, that's it. Alpha is zero after that point. Okay, it's just not accelerating anymore. There's no angular acceleration anymore. Okay, and so yeah, this is small. It's whoops. This one is small, okay? It's this one that you want, all right? And so here's that formula, and I asked for how far is the bottom of the test tube. That's R, the radius, okay, of the turn, okay? And just, dividing omega squared, both sides by omega squared, to get R is equal to AC divided by omega squared. Well, AC, you just found that. That was that 30,000, okay? And omega, that's the final angular velocity. We found that above. It was 5,000 RPM, but if you go up here, 5,000 RPM turned out to be 523.6 radians per second. Okay, and so 30,000 divided by 523.6 squared, that turns out to be 0.11213. Has to be MKS, everything else was MKS, so it'll come out in MKS meters, and so that's in meters, and so it'll be 11.2 centimeters. Okay, ask yourself, does that make sense? Yeah, test tubes, they're not longer than 10 centimeters, and so they will comfortably fit in there, and the bottom of the test tube would be 11 centimeters from the axis. Okay, again, I couldn't find that information in the specifications for this centrifuge, but that makes total sense to me. If I gotten like a meter or 2 meters, that makes no sense, because these things are not like 2 meters. I guess if they were 2 meters in radius, they'd be 4 meters in diameter. That would be insane. Okay, 10 centimeters makes sense. Okay, now while the centrifuge is spinning up, there is an angular velocity, and there's an angular acceleration, and therefore there's a tangential. After it's spun up, alpha is zero, so all of the acceleration is that centripetal acceleration. But while the centrifuge is spinning up, there is a little bit of tangential acceleration. You might say, how big is that? Well, it's just r times alpha. R we just found, it's that 11 centimeters, or 0.112 0.13 meters, okay? And alpha we found above was 11.6 radians per second. So if you multiply this out, you get 1.3 meters per second squared for your tangential acceleration, and that's tiny, okay? I mean, the acceleration due to gravity is 10, and this is like a little more than a tenth of the weight, okay? Compare that 1.3 to the 30,000, and I think you would agree that the centripetal acceleration is much, much bigger than the tangential acceleration, okay? And this is almost always the case. It's almost always the case, okay? I don't want to say always because I can think of situations like artificial situations where it wouldn't be. But you know, if you're talking about a centrifuge, your centripetal acceleration is going to be much larger than any tangential acceleration as the thing spins up, okay? All right, so there you go. That answers the question, how far are the bottom of the test tubes from the axis? About 11.2 centimeters. All right, last question. How fast is a point at the bottom of the test tube moving at maximum speed? Okay, so you know, if you were like a speck at the bottom of the test tube, okay, or yeah, at the bottom of the test tube, as it's turning, you know, you're going so fast, like so many meters per second. Okay, linear velocity. Not talking about the angular, but just the linear velocity. I say, well, how fast is that? That's called the tangential velocity. Okay, and so how big is that tangential velocity? That's obtained from the angular velocity by just multiplying by r. Okay, that's the general rule. You take the angular quantity, multiply by r, and you get the linear quantity. Okay, so the angular quantity is angular velocity, multiply it by r, and you get the linear velocity. Okay, well, we have r from above, we have omega from above, and if you multiply them together, that turns out to be 58.7 meters per second. Okay, so that's pretty fast. That these things are really trucking it in there. Okay, and if you convert that to kilometers per hour, I didn't ask you to do that, but just to give you an idea, that's 200 kilometers per hour. Okay, and if you're not used to kilometers, you know, like 55 miles an hour is about 100 kilometers an hour. Okay, and is that right? No, 65 miles an hour is about 100 kilometers per hour. Okay, so this is twice that speed. Okay, so you know, like 120, 130 miles an hour. So that's a crazy speed in there. Okay, so I don't know if you've ever used one of these before, but you have to close the lid before it starts to spin up, and that makes sense because if you put your fingers in there as these things are spinning, you're not gonna be happy about that. Okay, because they're really moving in there. They're spinning 5,000 times every minute, so you might expect that. Okay, so there you go. There's a simple question in angular um, kinematics. Okay, and you might hear my dog barking. That's because the mailman just arrived with the mail. All right, so that's it. That's it for today. If you don't have any questions, we can just call it a class. It's a little bit short, but we're doing pretty good with time as far as the course is concerned. We're on the last topic, and you know, once you're finished with that video, we're done with all the topics. Okay, so you still have to do the dynamics, and the dynamics are a little bit more involved than this. Okay, so you know, it's about another week's worth of stuff, and then we have Thanksgiving in there, which is just a couple of days, and then we have the final week. And the final week I'm going to use to, of course, just practice for the, like we have been doing, just practicing for the test. Okay, and so let me just see here if there's any questions. What day is the last test on? Tim, I don't remember. Look in the syllabus. I don't want to say something and then be wrong about it. I'm gonna guess that is it December 3rd? Let me see if I have you know what, I have the syllabus here. Just if you give me 1 second, I can answer that question. Oh wait, I've got the Physics 101. Well, yours will be the day before, so December 4th. I'm pretty sure it's December 3rd. You know what? Let me check, because otherwise I'm going to say something wrong, and then everyone's going to say, "But you said." Well, that's true. Okay, I think it's December 3rd. Yep, it's December 3rd. It's our last day. It's our last day of classes. Okay, so December 3rd. So the December, I guess that would be December 1st, we would practice. Okay, we would practice, and then you know what? We might even Might even practice the Monday before that, which would be the not the Monday, but the Tuesday before that, which would be the Thanksgiving weekend. I don't know yet. I mean, I don't know how far we'll get. We may or may not need that extra day, but yeah. So that answers your question, I think. Okay. Whenever you have questions like that, always just go to the syllabus because the syllabus has all that kind of information. Okay. Does anyone else have any other questions? Otherwise, we're done here. I'll wait a few seconds. All right, looks like everyone, no other questions. Everyone okay then? All right, let's call it a day. Bye bye, everyone. I'm going to end this